Okay, perfect. So, yeah, I mean, let's start. So, I mean, there was a 1 week pause, and we are starting today again. And I believe there will be pause of 1 more week next week because there is some event by SG Innovate and Ionic and I think some guys at Security. And so because of that, like, I think the next session will be on 25th of April. So far we have covered classical error correction, basics of quantum error correction, stabilizer formalism, and we also covered Tori code, introduction to topology, topological quantum codes, bosonic codes, subsystem codes. Today we will cover approximate quantum error correction, fault tolerance, and decoders. There are some of the references, like not the exhaustive list. I mean, sometime I mention some of the references when I'm presenting. So, like as always, I will first recap what happened last week. Then very briefly, I will talk about this notion of approximate quantum error correction. So far we have been talking about like quantum error correction, what and what does it mean to do approximate quantum error correction. Then quantum fault tolerance, this I will cover in detail. And decoders I will cover slightly, and next week I will continue talking about decoders. I mean, as you can see, like here, decoders will be continued. And then I will summarize. So let's recap. I mean, before I recap, I would just like to mention that during recap, I will be using some of the terms that we learned from topology, because we learned about topology last time, like application of topology for quantum error correction. So if you don't remember, please, don't run away when I'm talking about recap, because I mean, that will be a bit mathematical. But then after that, for these parts, like, you do not need to, like it will not depend much on topics from topology, like homology and cohomology that I discussed before. Okay. So just as a recap, so last time we discussed like in the topological language, what is a qubit? Basically, lies at the intersection of every one cell and every one co-cell. So one co-cell is just the dual of the one cell. And as we learned before, that you have a lattice and you have a dual lattice, and at their intersection, basically, so dual lattice here, like is basically this dotted line, and the actual the original lattice, primal lattice, is this these dark lines, and you see that at their intersection, our qubits are present. So, I mean, in the language of topology, you can say that every one cell and every one co-cell, when they intersect, you get a qubit. I mean, that's where that's how you represent qubit. And tensor product of poly-Z operator that we represent via one chain. Tensor product of poly-X operator, that is basically one co-chain. So it's a one chain on a, you can think about, like it's a dual of one chain. It's on a dual lattice. So this is your Z operator, this is your X operator. Their commutation relation is captured via the inner product, which is defined modulo 2 of the corresponding cells and co-cells. And then we also discussed about the notion of placate generators in this language. So they are basically associated with two cell and defined as a Z chain operator Z delta C, where delta is the boundary operator. Vertex generator is X delta tilde P tilde, and their commutation relation is here. And actually using fundamental lemma of homology, you can prove, and the definition of co-boundary, you can prove it, like that we discussed last time. Logical Z operators, they are non-trivial one cycles. Logical X operator, they are non-trivial one core cycles. Then logical Z operators, they are basically defined as elements of the first homology group. X operator, elements of the first co-homology group. So these are like Z, and then this is X1 and X2 operators. And any logical operator, that's basically, you can multiply it with a boundary term, which is nothing but a stabilizer, and it still remains a logical operator. Then we talked about also Z-type errors, and they are represented by Z chains, and errors are detected by measuring the vertex stabilizers. Basically, they don't commute, like you have one here instead of 0. X-type errors, same story. Now, like you have X cochains, and here you have Z like X stabilizers, and they should not commute. So when they don't commute, you get that's how you detect the error. And like to correct it, basically you apply the right chain such that together they form a boundary, which is a stabilizer. But if you do not do that, then that will cause a correction failure. Then we also discussed about analog, basically bosonic codes, and there we discussed about position shifts and momentum shifts. We also discussed this notion of analog stabilizer codes, which is, and you can think of as, defined over reals instead of over, two-level systems. And here you have K logical modes, you have N physical modes, and it can detect errors acting on at most D-1 of the modes and correct errors acting on at most D-1/2 floor of that modes. There exist analog versions of qubit repetition code, 412 code, source 9 qubit code, 5 qubit perfect code, surface codes, and so on. Then we also discussed the 4-mode code, like the analog version, and it's the analog of the 412 code. And here you have basically, these are the stabilizers, and they basically, this is the code space is defined like this, and you can basically take these terms in the exponent down, and they are called nullifiers. And nullifiers basically nullify it, so you get 0. So if you don't get 0, then that's how you will detect an error. So that's it. So if you don't remember, what we discussed before, you can watch the tutorial. And but you can do that later. But for the sake of what we are going to discuss today, even if you don't remember much, I will be talking about some of the concepts again, wherever required. I will not. And then there will not be much dependency on what we discussed before. So let's with that statement, let's move to discuss the notion of approximate quantum error correction. Very nice. So we know that in the error correcting codes that we discussed, we have this notion of you have this whole Hilbert space. And let's say the Hilbert space is this big room, but your code basically is a subspace, and everything else is just if your quantum state goes there, it is basically has some error. And the job of quantum error correction is to tell this guy to go back to basically error-free room. So that is all there. Basically, this is the room where, all the error-free guys live. But if you go here, basically you are committing some crime. So basically, through error correction, your job would be to send it back, send the quantum state which has suffered noise back. Let's say you can send it from here or here or here. And so you can detect the error and then you can correct the error. And in the process of sending, you do not want to, have some logical error. Like you can send it here, but let's say you send it here and in the process you apply a logical X gate or Z gate. So that is not allowed. I mean, if you do that, then that's considered logical error. Then, yeah, so let's say, so in any error correction, like you can think about error correction operation as you have some encoding map, and so encoding map basically takes your quantum state to row C, like which is in this subspace here, and you have some error E acting on it, and the error can whatever, like take it somewhere else. But then you have to apply a recovery map, and if the recovery map R of E of a row C basically is proportional to row C, then you are okay. I mean, why proportional and not equal? Because it need not be, like trace preserving map. And so if that happens, then, like you are able to correct the error. And in fact, somebody like basically Neal and Laflamme, they found the exact condition, which are necessary and sufficient condition for error correction. So let's say your code words are basically, when you map, let's say these are your code words. I mean, so these are your logicals, 0, 1, 2, like, these are your logical states. And if let's say the cross decomposition for your error map is given as, like this EI and EI dagger using this cross representation, then as long as this quantity here is some Hermitian matrix element times Dirac delta function, Kronecker delta function, then you are okay. And so I mean, like, why it should be the condition? I mean, like the proof for this, you can look in Nielsen and Chuang, but intuitively you can think about this delta function is just to make sure that like you should be able to distinguish between different kinds of the different errors that happen on orthogonal states should be distinguishable. And this Hermitian matrix CKL you get there, I mean, it's not identity because the cross operators, I mean, this cross representation is not unique, like it's unique up to, I think, only you can say, like unitary. So because of that, we get this term here, like, get the Hermitian matrix here. So this condition that we have here is called the Neal-Laflamme condition for error correction. This is necessary as well as sufficient. So you can be given any error correcting code, you can find out what are your phi I and phi, what are the different phi I, like, how do you map your different basis states like 0, 1, 2 using this code. And then you can write your given error, error map. You can write its write it using its cross representation, and then using these cross elements EK dagger EL, you can calculate the term here. And if it turns out to be some Hermitian matrix element times Kronecker delta, then you are okay. Otherwise, your code does not satisfy the necessary and sufficient condition for quantum correction. So that is nice. But that's like, look at it in more detail. I mean, goal of quantum error correction is to preserve a quantum state despite the presence of decoherence. But then somebody could ask, how much will it cost to provide the desired robustness? Let's say I want to preserve it, but I do not want to, so let's say I start with some state rho, and, I mean, after correction and everything, if I get a rho tilde, if rho is equal to rho tilde, I'm happy. But let's say rho is not rho tilde, but like rho is approximately equal to rho tilde. Maybe then also I will be happy. And then, so one can ask the question, let's say I do not want complete robust, complete error correction, but what if, like some error correction? The other question somebody could ask, for a fixed cost, what is the best achievable performance? Let's say I have, like, I do not have 5 qubits to encode one logical qubit. I have only 4 qubits. Can I still do some error correction? So these are very sensible questions in the NIST, because we do not have too much resources. And the question is, with the limited resources, can I still do some error correction? And so you can think about this question of this quantum error correction as some kind of a engineering problem, where we are asking about cost performance trade-offs. I mean, if you put lot of cost, then there will be better performance, but less cost, then you can understand. So a generic code will correct the errors, but with a high cost in terms of resources. And a physical realization, basically, but on the other hand, in experiments, we have some particular errors, like we do not have, generic error. So, I mean, maybe you need to design error correcting codes which protects against some particular kinds of errors, which we know that are more dominant in our experiments. So for this, there is notion of approximate quantum error correction was developed. So here the QEC criteria are not perfectly met. So this QEC criteria that we discussed, this is not perfectly met. There is no analogous definition in the classical error correction. And why? Because quantum states need not be orthogonal, they can be nearly orthogonal. And there was this very nice paper by Debbie Leung and others, where they proposed this notion of approximate quantum error correction. So we know that if, let's say, you have one logical, you have one qubit, and if you want to encode it, let's say, as a logical qubit, then you need 5 qubits, and the distance is 3. But then Debbie Leung and others showed that, let's say, if you are interested in protecting your qubit against amplitude damping channel, then, I mean, you do not quite require 5. Even if you have 4, you are okay. So this 4 can also do your job. And they talk about, they also come up with analogous condition for the approximate error correction criteria. So I mean, it's a very nice paper. It's good to read. And let's say, I mean, whenever you see a nice code, or let's say a nice family of code, you can ask a question. Let's say, I mean, can I, lower the resources? And can I, think about making it amenable to some particular noise model? And these questions will be very much, I would say, relevant question in the coming years. And because, I mean, and not much research has been done. I mean, research has been done, but I think there is a lot of room here for understanding approximate quantum error correction. Okay, very nice. Good. So now let's look at quantum fault tolerance. So without quantum fault tolerance, no quantum computing. I mean, we need it. Quantum fault tolerance is the resource that is very much is required. So I mean, not a resource, I would say, it's more like a procedure, you can say, that without fault tolerance, you can. It seems that NIST does not have much hope. I mean, based on the many negative results recently. So we need to think about achieving fault tolerance. So what is this notion of quantum fault tolerance? So let's try to understand this. So arbitrary good quantum computation can be achieved even with faulty logic gates. So that's what fault tolerance is. Like, there are individual components and they are faulty, but then there is some tolerance, and that's why it's called fault tolerance. Provided only that error probability per gate is below a certain constant threshold. So obviously there is tolerance, but I mean, tolerance cannot be, like beyond the limit. Like, some small, let's say if there is error beyond some error probability below some threshold, then fault tolerance can be achieved. So let's try to, like understand this. So suppose we are given this circuit. This is a very common circuit. Many of you must have seen. You start with hard mode, apply C0, and it will prepare a Bell state. Bell state, many people like to prepare for many different tasks. But suppose every component, each component here fails with probability at most P. So let's say the failure probability at most P, like, then the question is, what is the error at the output? Now, to calculate the error at the output, like you need to, so there will be no error at the output if none of the components fail. And what is the probability that none of the component fail? So what is the probability that, like one component fail? So that's P. What is the probability that one component does not fail? So that's 1 minus P. There are 6 components. So what if the probability that none of them fail? So 1 minus P, 1 minus P, 1 minus P, 1 minus P. You multiply them 6 times. And what is the probability that, so what is the error probability? So it's 1 minus the probability that none of them fail. So you take 1 minus everything. You do this and you get, like the leading term is order P. Why? Because P is less than 1. So P squared will be less than, less than P. So you see that if every component fails with probability at most P, then the output has error order P. And everybody can see this. So the question is, can you reduce P to P squared? Because when you do P squared, then life is good, because then you have found a procedure using which you will ask it to go from P squared to P4, P4 to P8, P16, and so on. So this is, like a fault tolerant implementation of the circuit here. So we will use 7 qubit steam code. I will explain what this code is to do the fault tolerance. So you have 0, 1 qubit, you encode it as 7 qubit here. You see here, right? 7 qubit. 0, you have 7 qubit. Then, so basically you need to fault tolerant prepare the 0 state. Then you need to correct it, because when you prepare, there will be some error. Then you fault tolerantly apply harder mode. That will cause some error. Then you will again correct it. Then the question is, here I did not implement anything. So why did, I still error corrected? So the answer is that when your qubit is there, even if you are not doing anything on it, it's not lying there and saying that, please, because you did not perform any operation, I will not have any error. There will be error. So you need to error correct it. And then you apply your C0 fault tolerantly, and then you correct it. And then you measure it fault tolerantly. So these are the components. Every component has to be done fault tolerantly. And that's your basically fault tolerant implementation of the simple circuit. Very nice. So the idea is that, let's say if every component fails with at most probability P, we want, after doing all this mambo jumbo, we want this to go from P to P squared. Otherwise, if it does not decrease, then better, I would just be happy with my old circuit. So that is the idea. So on top of that, there are certain things that we have to keep in mind. Just performing this kind of error correction periodically is not enough. Even if you keep on performing error correction, if you do not perform it right way, it can cause problems. So for example, the encoded gates that you have, they can cause errors to propagate. How? So you have some error here, and you have C0. And let's say it's an X error. So because of X error, your 0 will become 1. Now this C0, this has basically took the error and brought it here also. And it's definitely present there. So now 1 error becomes 2 error. So my friend David basically always says that better late than a noisy C0 gate, because like a noisy C0 gate, it like it I mean, it's not really noisy, but like the noise before the C0 gate, like it made everything so bad. So you have to design gates such that a failure anywhere during the procedure of implementing gate can only propagate to a small number of qubits on each block of the encoded data. So like whatever error that you have, so you should design blocks, and I will explain what it means, such that your errors should not like spread too much. If it spreads too much, then that can cause problem. And then the other issue is that error correction itself can introduce errors. So you have to be careful, like you need to do error correction in a nice manner, so that when you do error correction, the errors can come. So it's like a game where errors are coming and you're trying to correct them. And you should be trying to correct them in a manner that the rate at which you are producing the error and the rate at which you are correcting them, in the fight between these two, the rate at which you are correcting them should win. Otherwise, your decoherence will simply kill your quantum state. So what is the meaning of error propagation through a circuit? So we showed this thing here, right? So basically, the way you can think of it, like you had this, you started with something, and then there was, like some X error here, and then you implemented your C0 U. But you can write this as U X1 U dagger U, right? Because I can just add an identity here. And basically you can calculate U X1 U dagger if U is C0 is X1 X2. So you can get X1 X2 U. So you can think of it as there is a actual C0 being implemented, but instead of one error, now I got two errors. And you can perform this. So this is like basically just conjugation. So you can see what happens when you want to, let's say, implement S gate, and you have some X error or Z error, and because of that, like you will have certain errors introduced. So you can think of it as like, as if the C0 gate was implemented correctly, but an X error occurred on both qubit after the C0. Let's say if you want to implement X gate and some X error was there, no problem. I mean, it's okay. But I mean, no, if you want to implement X gate and say X error occurred, so because of that, like you did not implement anything, but you wanted to implement the X gate, so effectively an X error occurred. But let's say if Z error was there, then the error that occurred effectively was the minus Z, and so on. Like, I mean, you can calculate. It's just this simple calculation which can tell you what, given an input, what will be the output for a particular operation. So here we had X1, like X1, and the C0 was U, and you got X1, X2 there. So you have X1, X2, U. So apart from U, you have some extra thing, and that extra thing is the output that you have here. Very nice. So now the question is, what if here the C0 gate did not fail, but what if the C0 gate itself fails? Now in that case, you have to think of, that. So you have to represent it using your C0 gate is now some quantum operation E, and let's say U is the noise-free implementation. So then you can write your E as E, like map U and U inverse. So it's as if, you should write U inverse here. So you can add identity, right? So it's as if you implemented U, but together with U, because of your noise, this extra, idiot also came, like it, which you did not want there. And so this is the noise. So based on this, we want to, talk about what does fault tolerance mean? Like, what is the fault tolerance of a procedure? So fault tolerance of a procedure A is a property that if only one component in the procedure A fails, then the failure causes at most one error in each encoded block of qubit output from the procedure. So you will have some procedure, and we have different blocks. But every error that occurs, it should cause error in at most one block, not in every block at most one qubit. If it causes error in more than one qubit, then that's problematic. So let's look at, suppose we want to implement fault tolerant C0. Okay. So the 7-qubit Steen code, let's say we use 7-qubit Steen code to implement our C0 fault tolerantly. So this is the, the stabilizers for Steen code. And if you remember, the first lecture tutorial, there we said that every time you give the generator, you basically completely explain your, that's like a complete description of your code. So this is your Z operator, logical Z, this is your logical X. And yeah, and using like this code, basically Steen code, one can try to compute, whether you benefit, what will be the error per component, such that, when you go from your physical circuit to a logical circuit, you benefit. So this is your fault tolerant implementation of your C0. So you had, you encode, then you have C0, and you have syndrome measurement and recovery. This is the circuit. So let's say initially the error was order P. So let's call it P. And when you go to the second level, like what I mean by second level, when you encode it, your error should become order P square. But when you say order P square, you are actually, there are some constants that you are hiding. And these constants are very important, right? So you are going from P to CP square. And you will benefit only if, when you go from P to CP square, P is greater than CP square, right? If otherwise, let's say if the constant is too big, then, you basically have not benefited. So what it means that, this P will cancel here, and this means that P should be less than 1 by C. So this P that you get here, that is called the threshold. So every experimentalist, let's say when you come up with a code, they are interested in this number, this one number. What is the threshold? And this number basically captures when you have the logical circuit, when you have the physical circuit, and when you go from physical to logical, what is the error below which you benefit? Otherwise, if you don't benefit, then why go to the, the logical implementation? I could have just run my old circuit. So for a Steen code, this is 10 to the power minus 4. For surface codes and all, it's 10 to the power minus 1. Actually, many of, okay, I will talk about that later. There is something that I will discuss later. So the idea, so I will talk about this beautiful idea called, the concatenated code. And based on that, there will be a theorem that will follow, which is the threshold theorem. So let's say you start with your physical circuit and you encode it. And then you get a new circuit, which is encoded. But then you can consider every component in your encoded circuit as physical component. And then you can encode second level. And then you can go, third level, fourth level, fifth level, and you can just keep on concatenating it. Basically, at every level, I am considering the circuit which came from the previous level as physical circuit, and I'm using it to, get a logical circuit. And let's say I keep on going. And why I would like to keep on doing this? Because when I had, when I go from, every time I go from, physical to logical, the error I had was P, and the next time you had the error was, CP, order P square. And given, P is greater than CP square, if I go higher, again, I can follow the same procedure, and I can send this P square to P4, P8, P16, and so on. The error can, keep on going down. So basically, let's say that initially the error was the concatenation level C0, error is P, C1, CP square, C2, C this thing, CK error. So, but then whenever you are going from a particular layer to next, one level to next level, there will be some resource requirement for it, because you need to build it, the logical circuit from the physical circuit. And let's say D be the constant representing the max number of operation that you need to, get an encoded gate, and whatever error correction and so on. So initially you had circuit with, let's say, size Pn, and then you went to the next layer, and so you require, so here the resource requirement was, Pn. When you went to the next level, the resource requirement was Pn times D. Then here Pn times D squared, and so on. Here it will be Pn times dk. So you see that the resource requirement is going, exponentially in D. Exponentially. But then, so there is this question, what you want is, let's say your goal is to simulate, you have an original circuit where there are Pn many gates, n qubits, Pn many gates, and you want to simulate with accuracy Pn, epsilon. And we know that if you want the final accuracy to be epsilon, then individual gates, they have to be, epsilon by Pn. Because if you see the very first circuit that I showed you, every gate that error that will add, and because of that, if each of them they are less than epsilon Pn, let's say the error, then only the final accuracy will be epsilon. So you see here that if you go to kth level, you can bring down the errors to this much. So you have this thing less than epsilon by Pn, which means your 2k, you can take 2k here and take the log, and you will get, like, 2k should be greater than this number. So whenever P is less than P threshold, which is 1 by C, you can find such a K. You can find a K such that this is possible. Now, somebody can ask a question that we started with circuit which had, size Pn, and when you went to level K, the requirements was Pn e to the power K. Now, how large is this circuit compared to Pn? So don't worry, it's not very large, even if it looks like exponential. Actually, you have only polylogarithmic overhead. What this means, you look at it here. You had here, so can I copy here? Yeah, so this is it. And let's, sorry. Yeah, and let's take the, so this is the resource requirement. I think I can just write it here. So there is initially started with Pn, and when I went to kth level, it was Pn d to the power k, right? But you can write d to the power k as 2 to the power k log d, right? So Pn d to the power k is basically, let's say, log of Pn by epsilon. Basically, it's this number power log d, right? Because this number is 2 to the power k, right? So you just take power log d, and original circuit has size Pn, so this will be Pn times this number. So original circuit was Pn, but you only require polylog overhead because this is constant, so don't worry about it. And this is your log n. So basically it scales like, like poly log Pn and some constant, like Pn. So you see that as long as your k is like, error is below a particular limit, like, level, which is the threshold, by using a circuit which is only polylogarithmically larger than your original circuit, you can simulate any desired accuracy. So this was the beauty, of the threshold theorem. That whatever you give me accuracy, and as long as your circuit components are below the threshold, I can achieve that accuracy. So then the question is that how difficult is to achieve this this threshold? Actually, many people like John Martinis and others, they already got their circuit components below the threshold. So then one can ask the question, what is the issue? I mean, like you just build all of them together and, like you achieve any arbitrary circuit which have, like error below the epsilon. So even if, like in isolation, your qubits and gates, they have error below the threshold. When you combine and put them on a, chip, it's a new mess. And like they start behaving in a very nasty manner. And so the challenge is to scale, and while scaling, keep the error of the every component below the threshold, maintain it below the threshold, and then only you can get the epsilon. So that is the actual challenge, because there are so many wires and this and that and small chip and qubit and all. And I think experimentalists will better know, how challenging this problem is. So this is the fault tolerance theorem. And and the one thing that you can take away from this course is this fault tolerance. Like the quantum computation with arbitrary small error is possible, given every component of your circuit, the scale circuit, is below some threshold. Yeah, if you can maintain that, it's possible. This is a very remarkable result, because many people initially thought that it will not be, quantum computation will not be possible, but this was the result, which I would say changed I would say the course. Okay, so then let's look at how will you implement your Hadamard. So this is how you implement. This is your Z, this is your X. Your Hadamard will change X into Z. So Hadamard is just basically Hadamard on each of the single qubit. If you implement that, it will change your Z to X. So it's a very simple implementation. Now let's say this Hadamard here fails. That's not a problem, because this Hadamard here is not talking to any other Hadamard. So even if it fails, it fails. And and we don't have to worry. According to our definition, like every error causes at most error in any given block. So there is at most one error, right? No problem. Similarly, S, no problem. It will, because it has this structure. How do we implement control knot? That is also very easy. You just take two blocks. Now one can ask a question that suppose you have errors which are error here. Because of this C naught, you will get error here also. I will say no problem. Why? Because at most one error in a given block. Now this is a separate block. So this property that like an encoded gate can be implemented in a bitwise fashion. This is known as the transversality property of the encoded quantum gate. And we have transversality for in the Steencode case for control knot, S, everything. But this is not a universal set of gate. What about your T gate? And as it turns out, again, the same guy, Neal. So Neal you find many places, right? There was a Gaussman-Neal theorem, then Neal-Laplamp theorem, and again this Eastin-Neal. So what they showed that you can, if you want to achieve, let's say, if you want to do universal quantum computation in a fault-tolerant manner, then not all gates can be implemented transversally. Like you cannot implement all gates transversely. Like maybe you can find a gate, where some of them can be implemented, but then something will be left out. So here, T gate cannot be implemented transversally. So as Arthur Aker says in his, always that it's like trying to, you are, let's say, a poor guy with, very not so big blanket. And every time you try to cover one part of your body, like something else will remain uncovered. So it's like that. But then there are ways to circumvent the theorem using code switching, code drift. Like there are ways like magic state distillation and so on. So maybe you can look at, how to circumvent, or you can come up with, how can one try to circumvent the is thin as well. Maybe transversality is not required. Maybe somebody else, something else could be done. And yeah, like I mean, many people think that this problem of fault tolerantly implementing gates such that not much error spreads has not found like the best answer which should be there. Maybe like some of you can find a nicer implementation. Okay, so that's it. Now we come to the final part, which is about decoders. So if you recall, we talked about our logical Z operators and X operators. So an encoded logical operator must commute with all elements of the stabilizer group, must not be an element of the stabilizer group, and must satisfy the commutation and anti-commutation relation of the poly operator they encode. Right? I mean, we need this condition, like it should be in the stable. It should commute with the stabilizers, but should not be any stabilizers. I mean, we need that. And these are our Z, X, and so on. So in error correction, your goal is to identify the error operator to apply given the syndrome. And what is a syndrome? Syndrome is basically the value that you get when you measure your stabilizer, if you remember from like last tutorials. So you can apply the inverse of the error operator, that's also fine. And for self-inverse poly operator, you can apply the same operator. Why? Because poly square is like identity. But let's say, I mean, we saw earlier that let's say your error is E and you apply E prime such that they become a stabilizer. That's also fine. Why? Because you have error like this and you applied something like this. Together they became a stabilizer. And stabilizers basically do not, stabilize the code space. I mean, they do not take your element from the code space from outside the code space. So good, not a problem. So given some certain error, you can definitely, like correct it, and to correct it, let's say you apply something, which, like something like this, that will correct it. But then, I mean, maybe you ended up implementing, like correcting it something like this. And in that case, you ended up, like applying a logical Z error because there was some error, and then you implemented something which corresponded to a non-trivial loop, and in the process, basically environment caused some error, and you also caused some error, and together with these two errors ended up implementing a logical gate. So your state came to the code space. I mean, that's okay, but the way it came, that's not okay, because you ended up applying a logical gate there. So you can, for example, we'll say there is a Z error, you might end up applying a Z1, Z2, or Z1 times Z2, like depending on what correction operator you apply. Or all of them, they are equivalent up to multiplication by a stabilizer, it does not matter. So you can apply any of these correction operator, and let's say if you apply E times S, then there is no error. But if you apply anything, oh sorry, I think it's wrong here. Yeah, so in these cases, you will end up applying Z error, Z2 error, and Z1 times Z2 error. So there are these equivalence classes, which the equivalence classes is defined as to multiplication by a stabilizer. And there are 4 equivalence classes. And the task of the decoder is to find the appropriate equivalence class given the syndrome. Or in terms of, like topology or topological language, I mean, we know that if your correction chain and the chain corresponding to the noise, if C prime is not equal to C plus boundary, where boundary is a stabilizer, then you have an error. So the basically task of a decoder is to return the appropriate homological equivalence class for the error consistent with the observed syndrome. If you don't remember this, it's okay, no problem. Basically, what is saying that there are certain, out of them, there is only one correct class. And if you return your correction operator from the right class, then it's fine. Otherwise, you ended up applying that. You will feel like, okay, I implemented, the state is now in the code space, but it's there, but it has acquired error. And that's a bad error. It's a logical error. So what counts as a failure for a decoder? When it outputs a correction operator from the wrong equivalence class. So you design a decoder and then let's say leads to, some logical error, then that's the issue. Because in that case, it will end up causing a logical error. So there are, like family of many algorithms, like, maximum likelihood decoder, MW, minimum weight perfect matching, and so on. I think next time I will talk about MWPM, maybe one of them, let's see. And there is this nice small review paper by Arthur Pesa. Like it's a very nice, where he talks about some of these decoders. You can look at that. So as a summary, we talked about this quantum error correction condition. We talked about approximate quantum error correction condition. And we said that, 513 code is definitely good. But let's say if you're interested in protecting against amplitude damping, maybe you can, get away with 4 qubits also. So very nice paper, yeah. And then we talked about, let's suppose you want to implement this circuit, and if every component fails with probability P, then the error at the output is order P. And how errors propagate, that we also discussed. Then we discuss, this encode, this concatenations, where, like you go from label 1, label 2, label 3, label 4, and your noise basically goes down like this, yeah. And you want to decrease the amount of noise in the process. And there was this beautiful theorem called threshold theorem, basically, which says that you had error Pn, your error is, let's say, your every component of your circuit has error, the failure probability is below some threshold. Then if you have circuit with Pn polynomially many n component, let's say, or even called capital N component, then you do not require too many gates to achieve any desired accuracy. You only require this, like Pn times, or capital N whatever, times this polylogarithmic overhead, which is not large, right? At the moment, we are very poor people in terms of number of qubits and so on. So for us, it matters. But let's say once we reach, like, I don't know, we are talking in terms of trillion qubits and all, then or million qubits, like this overhead will not be much. So you see that, and you can achieve any desired accuracy. And this is what gives us faith that quantum computation is possible. Like whatever we write on pen and paper, like it can be implemented. And there are this fight between universality and transversal implementation. And we talked about this Easton-Neal theorem and so on. And then we also discussed about decoders. And we said that, the task of the decoder is to find the appropriate equivalence class. And this thing. So that's it. Next week, I will talk about some of the decoders. I will talk about connections of this quantum error correction with many-body physics, theoretical computer science, and some of you might be interested in also connection with black holes. It's not next week. I think it's wrong. It's next 2 weeks. So I think, Kianvi, maybe you can stop the screen recording.